I'll get started.
Yeah, okay, so now Alistair is going to tell us about partition.
Okay, so this is maybe this talk's a little more from the computer science perspective than many of the talks we've had this week. So we'll be talking about how to compute the various polynomials that we've been seeing this week. I should say, when I was thinking about what to say, I asked Cheyenne, what does he expect me to talk about, and I was expecting a short little list, and he sent me a complete lecture plan. So I'm following Cheyenne's lecture plan. So if you don't like it, you know who to blame. Okay, so and I also want to shout out to two of my students who, to the extent I understand any of this, it's largely due to them. Piyush is here as a fellow this semester. He graduated a few years ago and is now at the Tata Institute. And Jing Cheng is currently a student and graduating this year and looking for jobs. So, there we go. Okay, so I want to talk about a class of polynomials that we call partition functions, and they show up in motivated from statistical physics. So in a statistical physical system called a spin system, it's a discrete model that lives on some finite graph. And it has configurations which assign to each vertex of the graph one of a certain finite family of spins. So say spins 1 through q. So configuration is just an assignment of colors or whatever you like to the vertices of the graph. And then each such assignment has an energy, which we'll call h. And the energy has two components. One component comes from pairwise interactions. So you look at every pair of neighboring vertices and look at their spins, and there's some edge potential that tells you for any given pair of spins what the contribution is to the energy. And similarly, on every vertex, there is a potential that just depends on the spin of that vertex. Okay. And when you so in statistical mechanics, the key object is the Gibbs distribution, which I'll call mu, and this assigns to every configuration a probability that depends on its energy. Basically, it's e to the minus the energy of the configuration. Okay, and then there's a normalizing factor in that distribution. This z, which we'll be talking about throughout this afternoon. So this z is the sum of e to the minus h, right? And this is what I'll call the partition function. Now, it isn't immediately a polynomial, but if you change variable, then you get a polynomial, as we'll see in a minute. Okay, so another thing we're going to be sick of by the end of this afternoon is the Ising model. Okay, so the Ising model is a particular spin system in which there are only two spins, +1 and -1. And the energy of a given configuration is so you basically have a contribution of -b if both of the vertices on an edge have the same spin, and +b if they have different spin. Okay. And then there's also an external field which measures just the total sum of all the spins. So the partition function, just writing down what I had on the previous slide, you get this form. And so to make this look nicer, we're just going to perform a transformation in which beta is e to the minus 2b, lambda is e to the 2h. Pull out a factor that is, I guess I should have included this factor. There's an easily computable factor at the front here that just depends on the number of edges and the number of vertices. But basically, you're going to get a contribution of a factor of beta for every cut edge between plus and minus vertices, every edge that is connects a plus vertex to a minus vertex. And you're also going to get a factor of lambda for every plus vertex in the graph. Okay, so let me just do a little example. And so really this is a cut generating polynomial, right? Because S is the set of plus vertices. We're summing over cuts, right? Partitions of V into plus and minus, and we're allocating each cut a weight of beta to the number of cut edges times lambda to the size of one side of the cut. So here's a little example. This guy has 3 plus vertices, and it has 5 cut edges. So this will show up in the polynomial with a weight of beta to the 5 times lambda cubed. So looking at it as a cut generating polynomial, we sum over cuts, giving each cut a weight of beta to the k, where k is the number of edges in the cut, and gamma k is just a coefficient, which it counts them by weighted according to how large each side is. Now there's a fundamental difference between two different regimes here. So if we take beta less than 1, which is equivalent in the original parameterization to b greater than 0, then we're dealing with a ferromagnetic model, which means that it favors small cuts. So configurations with largest weight will be those in which all the vertices try to have the same sign. Okay. And conversely, if you take beta greater than 1, you're favoring large cuts, and therefore you want to get lots of alternations between pluses and minuses. So in the physics terminology, this is called a ferromagnetic model. Everybody is trying to be the same. An anti-ferromagnetic model, everybody is trying to differ from their neighbors.
Yeah. Is there a lambda to the k thing?
Well, I've absorbed the lambda into the gamma k. So I'm now looking at it as a polynomial of just in lambda with a beta as fixed.
It's not lambda to the k because like number of vertices on one side is not necessarily k. Number of edges that you cut is k.
Number of edges you cut is k. So inside here will be a sum over all possible values of the size of the number of guys on one side of the cut.
It's a polynomial in beta.
This is a polynomial in lambda.
Maybe.
Oh, I see. I'm sorry. You're absolutely right. This should be a beta, and this should be a lambda. I apologize.
Okay.
Yeah, I'm sorry. Most of the time I'm going to be okay. So this polynomial here, it's a polynomial in 2 variables, and it's going to be convenient for us to look at it either as a polynomial in beta with lambda fixed or as a polynomial in lambda with beta fixed. And I apologize for messing this up. Yeah. Okay. So other examples, which I'm not going to talk about in detail, which will no doubt come up tomorrow and throughout the semester. So for example, in the Potts model, instead of just having 2 spins, it's like a generalization of the Ising model in which you have q different spins. You have a field associated with each spin, and again you're looking at cuts, so you count edges that connect to unequal spins. So it's like a q-way cut generating polynomial. The hardcore model, the configurations are independent sets in the graph. So you have 2 spins, 0 and 1. You're not allowed 2 1s next to each other. So the allowable configurations are independent sets in the graph, and you weight each independent set by lambda to its size. Okay, and this is all of these things can be realized by suitable potentials. And finally, monomodimer model, where this is strictly speaking not a spin system because it's a model on edges, but you assign 0 or 1 to each edge of the graph, and your allowed configurations are matchings in the graph, so independent sets of edges. And again, you raise each to the power lambda to its, you weight each by lambda to the power of its size. And these are, this is really just the matching polynomial. Okay. All right, so why are partition functions important? So they show up in all these physical models. More generally, as we've seen with the Ising example, they're a generalization of counting problems. So you're looking at basically combinatorial generating functions. As we've seen, they're the denominator in the Gibbs distribution. Now, something that's a little less obvious is that their derivatives are actually observables in the physical system. So if you look at the derivative with respect to h of the logarithm of the Ising partition function, so you're going to get a 1 over z, right? And then you're going to get, because in the exponent you've got the field term h times the sum of the spins, this will come down when you take the derivative. And so what you're left with is the expectation over the Gibbs distribution. This is the Gibbs weight of a configuration. This is the denominator. This is the normalizing factor. So you get the expectation in the Gibbs distribution of this observable, which is the sum of the spins. Okay. And so generally speaking, and this is called the magnetization, the total sum of the spins. So generally speaking, because of the form of a Gibbs distribution where the energy sits in the exponent, derivatives of log z with respect to the various potential parameters, h or b or whatever, will always give rise to an expectation of some kind of natural observable in the system, some function of the spins or the pairs of spins. Okay. So that's another reason why these partition functions are important. And finally, something that I'll be spending quite a bit of time on today is z, the partition function, is connected closely with phase transitions in the model, which we'll see in a minute. Okay, so what about computing these polynomials? Essentially, any interesting counting problem in this class, any interesting evaluation problem for these polynomials is intractable in exact form. So it's number p hard to compute, for example, the Ising partition function, except at a very small number of more or less trivial points. I mean, beta 0, 1 or lambda 0. So these are extremal cases of infinite field or zero potential. And they're hard even pointwise. So you don't even have to play with the beta and the lambda to make them hard. And for those of you not aware of number p hardness, I mean, it's an analog of NP hardness or NP completeness for counting problems. So saying that proving that a problem is number p hard is tantamount to saying that we don't expect it to be solvable in polynomial time without a major breakthrough in complexity theory. So therefore, the game becomes trying to approximate partition functions. And the gold standard here is something called a horrible acronym FPTAS or FPRAS, right? So the difference between the T and the R is R stands for randomized, T just stands for time. So this is a fully polynomial time approximation scheme, fully polynomial time randomized approximation scheme. So these are algorithms that approximate z about as well as you can expect. So you give them the input of the graph. You also give them an accuracy parameter and an accuracy parameter epsilon, and you require an estimate that's within a 1 plus or minus epsilon of the true value of the partition function. And moreover, your running time should be polynomial not only in the size of the input, but also in 1 over epsilon. So as you require more and more accuracy, your running time doesn't blow up in a horrible way. Now, it turns out this is not an arbitrary definition. I mean, in fact, unlike approximation guarantees in optimization problems, it turns out this is, in fact, for a wide class of partition functions, this is a robust notion. So if I give you any kind of semi-decent approximation algorithm for a partition function, then I can bootstrap it to one that satisfies this condition, so one that is arbitrarily good. Okay. And by a semi-decent approximation algorithm, I would mean one that has maybe a polynomial here, like n to the 100. So if you can approximate z within an n to the 100 factor, then it can be bootstrapped to such an approximation. At least with randomization. A couple of other remarks that will come up. So if we want to approximate z, then it's enough to just calculate the marginal at a given vertex. So if you've got an Ising model, if you can compute at any given vertex the probability that it's plus, then that can be recursively applied to compute the entire partition function. And similarly, if you can randomly sample from the Gibbs distribution, then you can get an approximation algorithm for the partition function just by this observation. So if I can take random samples from the partition function, from the Gibbs distribution, then I can compute the marginal at a vertex and thereby the whole partition function. Okay. Right, so now I want to talk a little bit about phase transitions. One way to think about phase transitions is that somehow if you just specify the local potentials of the model, then as the size of the system goes to infinity, they are not enough to determine the macroscopic properties of the system. So somehow there's some non-determinacy as the system goes to infinity. So I'll make that precise in a moment, or more precise in a moment. And classically, there are two characterizations of phase transition that float around. So one of them is a probabilistic notion. So in probabilistic notion, you think of your finite. You think of a sequence of finite graphs going to infinity, and you imagine putting different boundary conditions around the outside, and as your graph goes to infinity, the Gibbs measure that's induced will actually depend on the boundary conditions. So there isn't a unique Gibbs measure induced by the boundary conditions. And the second notion is an analytic one, and this refers to the partition function z having zeros in the complex plane. So it's not immediately obvious why complex values should be relevant at all here, because, I mean, after all, everything's real. But we'll see in a moment why this shows up. So these are two different notions of a phase transition. Yeah.
It always gets zeros in the complex plane, right?
Sorry, everything is real, so it's not relevant why having zeros in the... It always has zeros in the complex plane, but the question is in what domain it has the zeros. Yeah. So the absence of zeros for certain ranges of parameters. Okay. So the rule of thumb is that if you have so since we're talking about computation, rule of thumb is that if you have phase transitions, if you have a phase transition in the model, then this should show up computationally as making the computation of the partition function harder. So in particular, we'll see that certain local algorithms fail, and sometimes even the problem becomes computationally intractable when you have a phase transition. Okay, so let's look at this in the case of the Ising model, and let's look at the Ising model, a special case on the infinite d-dimensional Cartesian lattice, CD. And we're going to look at this as the limit of finite graphs, so a limit of n 2n by limit of boxes minus n to n to the d. And it turns out that at zero field, when h is 0, the Ising model exhibits a phase transition when the interaction parameter b is above a certain critical value, which depends on the dimension, okay? And not otherwise. This is the only place where you get a phase transition. So let's briefly, this can all be made rigorous. It's not, I haven't spelled out details at all, but this is just to give an idea here. So first of all, let's look at the probabilistic characterization of the phase transition. So you look at your box, and in one case you look at putting plus boundaries around the box. The other case you put minus boundaries around the box, and you let the box go to infinity. And you look at what the what's the magnetization at the origin. So what's the probability? What's the expected value of the spin at the origin? And it turns out that if when b is bigger than beta critical, then these two values are different. So you actually get a small positive, or a positive spin here and a negative spin here.
Isn't that strict in the Polynomials?
Sorry?
True at the critical point?
It is, I think, true at the critical point. Yeah. Okay. So what it means is that even as the boundary recedes to infinity, there is a non-vanishing effect of the boundary felt at the origin. Okay, so for the analytic characterization of the phase transition, we look at the quantity that's sometimes called the pressure, which is log of, basically log of the partition function, normalized by the volume so that it's something that stays finite. So let's call that quantity psi. Okay. Turns out that this limit always exists, and it's independent of the boundary conditions. You don't have to specify the boundary conditions. And so, remember from a few slides ago that the derivative of log z is just the magnetization, and we're just normalizing it, so it's the magnetization per site. So for finite volumes, this quantity is just the expected magnetization density, magnetization per site. So if this guy is differentiable, what we'd expect is that so its derivative exists. And then if we're lucky, we can interchange the derivative and the limit, and we should get that the derivative is equal to the limit of the magnetization density, okay, which I'll call m of bh. Okay. So this is this condition is really saying that the observable m, the magnetization, behaves nicely in the limit. And in fact, for the Ising model on ZD, these two characterizations of the phase transition happen to be equivalent, because you can show that the right side, so the right and left-sided derivatives of the pressure always exist. And the right derivative is equal to the limit of the magnetization with a plus boundary, and the left derivative is equal to the limit of the magnetization with a minus boundary. And so if the derivative exists, then these two left and right derivatives are equal, and therefore the magnetizations are equal, and therefore in particular the spin at the origin is equal. So the Gibbs measure, and that's enough to in fact tell you that the Gibbs measures are the same. So you have this picture for beta less than the critical value, this mean magnetization behaves nicely everywhere. For beta above the critical value, it's not defined at 0. Okay, so h equals 0 is where you have a phase transition, and you have different values of the mean magnetization according to whether you're in the plus boundary or the minus boundary, or equivalently whether you're taking this derivative from the left or the right. So that's very roughly the connection. So how do we use all this to actually, how do we use these characterizations to prove the existence of a phase transition? Well, for proving that there is a phase transition at h equals 0, you typically use the probabilistic characterization. You explicitly analyze the limit of the magnetization at the origin with a plus boundary, and show that it goes to 0 when b is small, and that it stays away from 0 when b is large. Okay, and this establishes the existence of the phase transition at h equals 0. The thing I want to focus on, though, is how do we show that that's the only bad point? How do we show that there's no phase transition when h is non-zero? Right? And this is where I'm, so it's a long route there, but this is where I finally want to make a connection with zeros and zeros in the complex plane. So to show there's no phase transition for h non-zero, we have to show that this function psi is differentiable when h is non-zero. Now, this is a famous Li-Yang program from the 50s, and you know, first they proved a general fact, which is that so we want to show that that this function psi, which is the limit of log z, is differentiable, and it turns out that it's sufficient to show that z itself has no zeros Okay, so you want to find a region in the complex plane D, such that Z itself has no zeros in that region, and this is just for finite Z. So this is going to give us a finite volume condition to check. So if you have a simply connected open region that contains an interval of the real line, which is the piece you're interested in, and if you want to show that psi is differentiable, you actually can show it's analytic in this whole volume D, provided you can show that Z has no that any of the finite Z's have no zeros in that region. Okay, and then the thing that really makes this powerful is what they then proved, and this is what I'll call the Yang Theorem. So what they showed was that in the Easing model, for any value of B, the only zeros of the finite volume partition function, indeed this holds not just on ZD, this holds for any graph at all. So for any finite graph G, the only zeros of the partition function must have a real value of 0. It can only lie on the imaginary axis. Okay. And so applying the previous general fact with D being, say, the right-hand half plane, this will tell us that psi is real analytic on this axis, and therefore there's no phase transition. So what this condition does is it allows us to replace the thornier problem of showing that psi as a real function is differentiable on the real axis by the supposedly easier problem of showing that Z has no zeros in the complex plane. Okay. Showing that Z has no zeros in the complex plane. Okay, so let me the first actual math we're going to do is to prove this theorem. So prove the Yang theorem, and it's slightly easier to use the alternative parameterization. So let's I think I've got this the right way around this time. So I want to view Z as a function just of lambda, because remember we're looking at analyticity in H, and H corresponds to lambda under the change of variable. So I'm now looking at this polynomial, and I'll absorb this just as a coefficient. So I'm looking at a polynomial in lambda. And the claim is now that we've changed variable, rather than showing that the zeros lie on the imaginary axis, we're going to have to show that they lie on the unit circle in the complex plane. So the claim for Yang is for any graph and any value of the interaction parameter beta, all the complex zeros lie on the unit circle. And there's an obligatory joke that comes up when you talk about the Yang theorem, which is that Li and Yang, who won the Nobel Prize, not for this but for other work. So the day after the Nobel Prize was announced, the Chinese restaurant in Manhattan, where they met up to do a lot of their joint work, put a sign like this in the window, and presumably sales were boosted among those who know what Nobel Prize is. Okay, so let's prove the Yang theorem. So remember, this is an extremely general fact. So this holds for an arbitrary finite graph G, and we have the polynomial from the previous slide, right? This polynomial. And I'm going to, in order to prove this, we're going to consider the multivariate version of that polynomial. So now I'm going to give a different variable lambda to each vertex of the graph, so this will be the form of the polynomial. N here is the number of vertices in the graph. Okay. And I claim it's sufficient to show the following. So we want to let's define. Let's say the polynomial is Lie-Yang. The multivariate polynomial is Lie-Yang. If it has the following property, that if all of the lambda i's are in absolute value bigger than 1, so they all lie outside the unit circle, then the polynomial is non-zero. Okay, so this. Okay, so if we project back down to the univariate version, we set all the lambda i's to be equal to lambda, then it says that if lambda's outside the unit circle, we have no zeros. And then by symmetry of between lambda and 1 over lambda, so this polynomial is symmetric in lambda and 1 over lambda because basically the you're either looking at one side of the cut or the other side of the cut. Okay, so in particular, z of lambda is just lambda to the n times z of 1 over lambda. And so it suffices to show that there are no zeros outside the unit circle, which implies immediately there are no zeros inside the unit circle. Okay, so so this is what we want to show. Okay, so this goes by a nice induction argument, a combinatorial induction argument. There are many proofs of this. Actually, the original proofs were much less combinatorial, but this proof is this proof is attributed to Asano originally. So so how do we prove this? So we start off with the base case, which is a single edge. So our graph just consists of a single edge. There are two parameters, a lambda 1 and a lambda 2, and let's write down the partition function. So what's the partition function for this simple graph? Well, there are four configurations, right? Plus, 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 minus, minus, plus, and minus, minus. So the plus, plus configuration will give us a lambda 1, lambda 2 term, right? Because two pluses. The two configurations, plus, minus, and minus, plus, each of them will pick up a factor of beta from the cut edge between plus and minus. One of them will get a lambda 1 for this guy being plus. The other one will get a lambda 2 for this guy being plus. And then the minus minus configuration will give us a 1 because there are no cut edges and no plus vertices. Okay, so this is the partition function. And now for the partition function to have a 0, it must be the case that, okay, just solving the equation, lambda 2 has to be equal to this ratio here. So this thing is a Möbius transform that maps the exterior of the unit disk to the interior. So if lambda 1 is outside the unit circle, then lambda 2 has to be inside the unit circle. And therefore, if they're both outside, we cannot have a 0. Okay. Second simple ingredient is that if G and H are vertex disjoint graphs, their partition functions are ZG and ZH. If each of them separately is Lie-Yang, then since the partition function of the union of the two graphs is just the product of their partition functions, this is easily, obviously also Lie-Yang. And finally, we've got the inductive step, which involves merging vertices together. So we're going to build up any graph using from a single edge using this operation. So if we at some point have two vertices, so one with parameter lambda 1, the other with parameter lambda 2, and we're going to merge them together into a single vertex like this with parameter lambda. So we want to show that if this inductively is Lie-Yang, then this polynomial resulting from the merge is also Lie-Yang. So so let's fix all of the other, the values on all the other vertices, and all in the regime we're interested in. So they're all outside the unit circle. Then by our inductive assumption, the partition function of this thing it has the Lie-Yang property. So these coefficients A, B, C, and D are just computed from the effect of the rest of the graph. Okay. So these are some coefficients on the rest of the graph. And we'll have a term, for both being plus, a term for one being plus, one being minus, a term for one being minus, one being plus, and a term for both being minus. So we get a polynomial of this form. And since this has the Lee-Yang property, we know that this polynomial cannot be 0 if both lambda 1 and lambda 2 are outside the unit disk, since all the other variables are already outside the unit disk. And so
Confused. What are you inducting on?
I'm inducting on this graph already being this partition function already being Lee-Yang.
Okay.
And I can write that partition function in this form.
Okay.
I'll put it all together on the next slide. But yeah, okay. Let's look at this first. Right. So you start. So to get your final graph, start off with a bunch of independent edges. Each one is Lee-Yang, we know, and then their product is Lee-Yang, and then you merge them one by one to get the graph. Okay. Yeah. So I should have put this up first. All right. So okay. So now we're interested in the case where lambda 1 and lambda 2 are going to be merged, so they'll have a common value lambda, so we'll make that substitution. So we certainly know from this fact, we know that this guy doesn't have any zeros, right, if lambda's outside the unit circle. And therefore, this is just a quadratic polynomial, so the product of its zeros is d over a, right? And so it so since its zeros must be less than or equal to 1, d over a must be less than or equal to 1. And therefore, the new partition function that we get here, right, which is after all just a lambda plus d, right, because the contributions from configurations in which lambda 1 and lambda 2 are different, right? So these contributions go away. So the new partition function on the right-hand side has the Lee-Yang property. Now there's a detail here that we're dividing by a, so you also have to check inductively that a is non-zero, which can be checked as we go through by a similar induction. So the proof is very simple. Okay. Before moving on from this, I wanted to okay. So that so that definitely establishes the lack of a phase transition for positive field for the Ising model, but it's also a very finite result that we can use, and we will later on, which we can use computationally for finite graphs that have nothing to do with ZD. Okay, so I just wanted to, before moving on from Lee-Yang, I wanted to mention a little spin-off from it, which may or may not be interesting. So it's interesting to, as we know, it's interesting to think about what happens when studying geometry of polynomials. It's interesting to think about what happens to the zeros of the polynomials when under natural operations, and one of which is taking the derivative. So we know that this polynomial z has the Lee-Yang property, so its zeros lie on the unit circle. What happens? Where do the zeros of its derivative lie? And it turns out that you can prove that provided the graph is connected, the zeros lie strictly inside the unit circle. Not they lie strictly inside. So the Gauss-Lucas theorem will tell you that the zeros of the derivative lie in the convex hull of the original zeros. But that doesn't actually show that they that doesn't preclude them being actually coincident with these points, or equivalently of z having multiple zeros. Okay, zeros of multiplicity bigger than 1. as a result, once you prove that, and the proof of that goes via an argument that's quite similar, it basically follows the Asano construction, though it's a little more technical. And one of the exercises, we look at the base case of this.
So, but it's equivalent to prove that it has no multiple zeros.
Yeah, it's equivalent statement is that Z has no multiple zeros. Yeah. And notice it's trivial that you need connectedness here, because otherwise you just take two copies of the same graph, and it obviously has multiple zeros.
So one more question. So the Liang, it holds for all betas, or was it
Yeah, all betas. Well, ferromagnetic. So beta has to be
between
0 and 1. Yeah. Yeah, it doesn't hold for an antiferromagnetic. Yeah, that was. Sorry, I guess. I mean that. This Möbius transform here, right, only has this property when beta's between 0 and 1. Okay, so.
So do we know analogs for, like if beta is more than 1, do we have any structure?
Not that I'm aware of. Nice structure of it. Well, there's for the independent set. Sorry.
So the Möbius transform now takes the exterior to exterior, interior to interior. So you lose that nice symmetry, and zeros fly off.
And then, okay, so now, so for the experts in the geometry of polynomials, I'd be curious to know whether this fact is of interest, and if so, what can one do with it? I can tell you one thing you can do with it from a complexity theoretic point of view. So the fact that the derivative of z and z itself have no common zeros allows you to show that complexity theoretically computing the mean magnetization is just as hard as computing the partition function. So remember the mean magnetization is that the expected, it can be written as basically the ratio of the magnetization is the derivative, the mean magnetization is the derivative divided by z, right? So that's the quantity of interest. We have an extra factor of lambda here because we've changed parameters from h to from e to the h to lambda, so that just naturally shows up. So, so the point is that, so suppose I want to show you that computing the magnetization is just as hard as computing this denominator here. Then, now it could be that there are magical cancellations that make this an easier quantity to compute than this. And in particular, when lambda's 1, this is trivial to compute. So is that something that, I mean, when lambda's 1, you have 0 field, and therefore by symmetry the magnetization is just 0. Okay. So can this be easy to compute for any other reason? So the answer is no immediately from the fact we just established so the fact that the zeros of this guy lie inside the unit circle while the zeros of this guy lie on the unit circle means that they have no common zeros, and therefore you can use rational interpolation to compute these two polynomials given an evaluation of this a bunch of evaluations of this polynomial. And so you deduce that computing this thing is number p hard at all points, all interesting points, even on bounded degree graphs. Good. Okay. So that's
Analog for simplices for when three particles interact, when there are triangles or
not that I'm aware. I mean, an analog of what, this, or the Yang Theorem, or what? Not that I'm aware of. I mean, there are theorems that say which types of systems satisfy the Yang property, and they're fairly restrictive. So yeah, three-way interactions, I don't think.
There's a hypergraph.
Oh, I see. Yes, true. Yeah, good point. Yeah.
There are some hypergraphs, not as general.
Yeah. So for that's true. Yeah. So for hypergraphs, you can also prove Yang Theorem. But the range of betas that that you can handle depends on the size on the size of the hyperedges. That's actually another of the exercises. Exercise 4.
By the way,
Yeah.
a continuous version on the imaginary axis. Is it proved using this one? This kind of like discrete version inside of unit circle, and the continuous version. When you lie on the, is it proved using this one?
Continuous version of what?
When all roots lie on the imaginary line. Real.
Oh, but that's just it's a trivial mapping from the. Yeah. So no, this immediately implies because it's just a change of variable.
So I'm just curious. So that Hellman-Lieb, they were certainly aware about this proof. The proof of real rootedness of matching polynomial, because it kind of a bit similar to this.
Hellman-Lieb paper contains 4 different proofs of real rootedness of matched polynomial, one of which is reducing it to
I see.
Yeah.
the
Right.
They also have a reduction the other way, so they also
Yeah,
show
yeah,
that
yeah.
you can use the Harmony to prove that the Yang Theorem is certain.
But
Although the
Hellman-Lieb was later. Hellman-Lieb in 1960s.
No, it's
70.
72.
72. Yeah. So it's.
But I think this Asano proof was also around then, right?
Like the
Yeah.
same year maybe even,
I
71.
see.
But they're absolutely honest. They say that it's equivalent. Well, any true
Who
statements
said?
are
Hellman-Lieb said.
equivalent.
Ah, yeah. Okay.
Yeah, and they show the equivalence.
Okay. Good.
Right. So at this point, I've run out of slides. So I was going to now switch to the board. There's also the exercise. So I don't know. Let me just start. Yes. Sorry.
One more question or comment. So now there is a strengthening of Gauss-Lucas. Actually, there is a majorization result. So it's not just the inside of convex hull, but if you kind of augment to have the equal sum, that roots of derivative, even in a complex case, you can write as a double stochastic matrix times root of roots of the polynomial. So I'm just curious, that's a serious strengthening of Gauss-Lucas. Can it affect some kind of...
I don't know. I haven't looked at that. So it would be interesting to see whether that implies this. But.
Again, Gauss-Lucas is 19th century, so now there is
Right.
a stronger version.
Yeah, but here, remember, there's this combinatorial condition that the graph is connected.
No, I don't say that it will improve.
Yeah, okay.
Simplify, but you can get stronger condition than just inside. So there is kind of majorization.
Okay. All right. Okay. So let's. Right. So what I want to talk about the rest of the time is different methods for obtaining approximation algorithms for partition functions, and there'll be connection to phase transitions and to both types of characterization of phase transitions, so both to the probabilistic version and to the polynomial, the analytic version. So I guess there are three kind of generic methods that are widely used. So there's Markov chain Monte Carlo algorithms. There's algorithms based on correlation decay. And there's algorithms based on polynomial interpolation. Now, so these This is obviously, as its name suggests, this is a randomized class of algorithms. This is these two are both deterministic. The correlation decay algorithms are based on the characterization of lack of phase transitions by uniqueness of the Gibbs measure, and which means essentially that correlations decay over distance in the spin system. And polynomial interpolation is based on finding regions in which there are no zeros of the partition function. This is a method that's recently pioneered by Sasha and collaborators. So I'm going to briefly discuss each of these, again, with respect to our running example of the Ising model, and try to say a little bit about how they might be connected, and although that's very much work in progress. So, so first of all, let's start with Markov chain Monte Carlo. And I'm not going to say a lot about this because, in some sense, this has been around for a long time, and it's a topic in its own right, and it's got less to do directly with the topic of this semester. But I want to make some observations about it because, in many cases, for many spin systems, it's still the method to beat. I mean, somehow there are many cases in which this does better than anything else, but it's randomized, so trying to achieve similar performance to Markov chain Monte Carlo from these methods is tantamount to de-randomizing randomized algorithms for partition functions. And as we all believe that randomization isn't ultimately necessary, we should expect whenever you can do something with a randomized algorithm in polynomial time, you should be able to do it deterministically as well. Okay, so for the Ising model, and this is why I chose this example as a running example, the Ising model there's something interesting to say about all of these, even without leaving the confines of the ferromagnetic Ising model. So for Markov chain Monte Carlo, so what Markov chain Monte Carlo means that you do a random walk on the set of configurations. Okay, and usually it's a local random walk. So local random walk means that you, e.g., you flip one spin at a time. And it's easy to arrange the flipping probability so that you will converge to the Gibbs distribution in the limit. So arrange, define so that the stationary distribution of the Markov chain is what you want. Is the Gibbs distribution. And that's because basically if you just look at a particular spin, you can re-randomize that spin based on the current configuration of its neighbors. You know the correct marginal probabilities for it, and so you just plug it in. Now, if you try to apply this to the Ising model, you run into exactly on the wrong side of where you have the phase transition. You're going to get a problem because so imagine you have very strong interactions. You've got the phase transitions in effect. So the stationary distribution, the mu, the Gibbs distribution, kind of looks like it has two phases really. It has a phase that's mainly almost everything is plus, and a phase in which almost everything is minus with little imperfections. So, but any kind of local dynamics that's just flipping spins one at a time takes a very long time, an exponential time to, if you start off, for example, in a configuration like this, it takes you exponential time to make a transition. So, the naive approach, Markov chain Monte Carlo approach, does not work for this problem, and again, essentially because of the phase transition, because of the existence of long-range correlations, essentially. However, there is a trick you can perform here. So what you can do is you can transform the the representation of the Easing model to something that's called the high temperature expansion. And in the high temperature expansion, the configurations are now different. So now the configurations are subgraphs of G. Okay, so they're of the form, say, H V E prime, where E prime is a subset of the edges of the original graph, and you keep all the vertices around. Okay, so if my original graph looks like this, then I could have one of the subgraphs might be this guy. Okay. And a subgraph has a weight, and the weight is so the weight of the subgraph, the weight of H, will be psi to the number of edges in H, and eta to the number of odd degree vertices in H. Where this eta and psi are defined in terms of the original parameters. So psi is, get this right, psi is hyperbolic tangent of b in the original representation, which is the same as 1 minus beta over 1 plus beta in the reparameterized version we've been working with, and similarly for the other variable. Anyway, so and then what you can show is that let's call this new partition function z hat. So that's a function of these two new variables, and this is equal to a times z of beta and lambda. Same graph. Under this identification of parameters, where this a is an easily computable constant. Again, it's something that just depends on the number of vertices and edges of the graph. So that means that computing this thing is equivalent to computing this thing. And now, if you run Markov chain Monte Carlo in this new set of configurations, it turns out that somehow you don't see the phase transition. So this there's no obstacle anymore to this Markov chain not only converging to the Gibbs distribution but converging rapidly to the Gibbs distribution. So the fact is that local Markov chain on these configurations, on these subgraph configurations, right, converges to the Gibbs distribution from any starting state. In time, I mean, it gets very close, right? In time, polynomial in the size of the graph, and in 1 over eta. Okay. And by local dynamics here, I mean, okay, so your configurations are now subgraphs. What you do is you just pick an edge and you flip it. Either you if it isn't there already, you include it, or if it's already there, you take it out. And you do that with the right probabilities. You converge to the correct Gibbs distribution based on these weights. Okay.
Every beta? Or
this works for every ferromagnetic. Yes, every beta less than 1. Yeah. Yeah. So throughout, unless I state otherwise, the Easing model is ferromagnetic. Should have said that. Everything I've said is ferromagnetic.
sorry, one more question. E prime of H is number of edges of H?
Yeah, this is the number of edges of H. Maybe I can just take that out. Yeah. So this is the right. So the weight of the weight of this configuration would be psi cubed, because there are 3 edges in it. And then we look at how many odd degree vertices it has. Well, actually, it has all of its vertices are odd, so b eta to the 4.
If what I wanted to accomplish was just being able to sample in polynomial time from the Gibbs distribution, presumably I could have just added a global sign flip transition to the whole Markov chain. If I augment with some small number of non-local moves, can I avoid this?
Well, that's actually not. That's a bit of an open question.
Oh, really?
Yeah, whether the only obstacle is. Whether that's the only obstacle, it's basically what you're saying is that if we add those flips, then we, yeah. So in general graphs, this is not, yeah. Right. Okay, so, so this is true, right, for all values. This is true for all parameter values, okay? Actually, I guess I've already said that because I've included the right. So this is certainly for all psi in the ferromagnetic, right? For all psi. So there's a right. So this means that you can sample from this transformed Gibbs distribution, which then also means that you can compute this partition function by standard, reduction from reduction to sampling, and there's a minor detail that you do need. So you can't let eta go to 0. Remember, eta is the parameter that corresponds to the external field. So you do need a small external field here for this algorithm to work. In other words, you do have to allow odd degree vertices with not tiny probability as you move around in this Markov chain. But it turns out that if you, so you'd be fine, say, if eta is about 1 over n or something like that. This would still be polynomial. And it turns out that if you can estimate the value of this partition function with eta very small, like 1 over n, not a constant, but something that goes to 0 with the size of the graph, then you can also estimate it with eta at 0, because the two are very close. Okay, so I want to get into how you prove this, but except for one observation, and I'm making this observation to try to make connections with other parts of the program. So it turns out that when you, in the analysis of this Markov chain, something that drops out from the analysis in a natural way is that the coefficients of this polynomial, when viewed as a polynomial in eta, are log concave. So if we look at the polynomial sum, gamma k eta to the k, where these gamma k's, code up the dependence on psi. So this is the polynomial that counts subgraphs of a graph where k is with k odd degree vertices. So k is the number of odd degree vertices. Of course, k has to be even. So this is the polynomial that has only even coefficients. And
sum is on h. What is this? The fixed h and sum.
yeah, the sum is on h. So did I ever write down this? So the sum z. This polynomial, which I never wrote down, I've now realized. So this polynomial z hat g of eta, the sum over h of the weight of h. All right. This is just that polynomial viewed as a polynomial only in the second parameter eta. Okay. So something that comes out of the analysis of this Markov chain in a way that's a little convoluted, but it comes out very naturally, is that the sequence, so the fact that drops out is that the sequence of coefficients psi k is log concave. And one of the exercises is to do the same for the matching polynomial. So there's also a Markov chain for the for matchings. that also converges in polynomial time, and the analysis of that has the same property that as part of the proof, the analysis of its convergence time, you actually see that the matching polynomial has log concave coefficients.
But in matching polynomial, it's stronger than log concave.
Yeah, so ultra log concave. So I'm not sure if these proofs can be, these are basic, very elementary combinatorial proofs. I think they probably can be strengthened to be ultra log concave, but I'm not totally sure about that. We'll see in a moment in the exercise. Okay, maybe that's a good time to stop. I think I'm. So let's pause here. So I claim the prize for the most verbose exercises of the boot camp so far. But they're verbose, but they're not actually that hard. So so there are three. I don't know what to do. Maybe take a look at them and when are we supposed to restart? 3:45?
So this one goes till 3:20, including the exercise.
Another 10 minutes. How about I propose a slight reshuffle of that? So we'll take a break now and then give you a chance to look at these, and then we can come back and talk about them at the beginning of the next round.
Sounds good.
Okay, great. Thank you. We can. How about we? Is everybody okay with restarting at 3:35 instead of 3:45? So shifting. Is that okay? Okay, great. Thanks.